Right. So today we will going to talk about partially observable Markov decision processes, and this presentation is also partially made. So
partially observable.
Yeah, partially observable. So please be patient, and if you have any questions, hesitate to ask them. So today, what is? Let me talk a little bit about partial observable Markov decision process in advance. So why do we need them? I think it's probably evident because we every one of us usually is very limited in its power, in oneself power. So he or she doesn't see everything. She sees only a small picture in front of him and nothing behind him. So the partial observability, that is inability to see something in the real world, in the environment that surrounds the agent, is a really universal property of our world. But in the same time, this topic is not a mainstream topic in reinforcement learning. That's because two reasons. The first reason is that it's incredibly hard, much more hard than the usual or typical reinforcement learning problem. And the second is that there are so many papers on the partially observable Markov decision processes, but not in learning them. Only these papers are about planning. That is, the planning is a process when you are given a model of the world, that is a model of transitions. You know what is a transition function between states, and you know everything. You know probability of rewards. You know probability of observations. You know probabilities of transitions, and the task is to find, mainly to search for best possible policy. But in learning, you haven't access to the environment model. You don't know what is the transition function between states, and more to say, you even don't know what the states are. You, in some cases, you are just allowed to know what is the number of different states, and this is very limited information. So today, I will remind you a bit about Markov decision processes and show you some interesting examples. One interesting toy example why the partially observable Markov decision processes are a bit closer than we are used to think about them. Then I will introduce a partially observable Markov decision process mathematical definitions, and we'll talk about what will going to happen if we ignore this partial observability, this property of partial observability. And the last part of my talk will be very limited and very selective introduction of learning methods in partially observable Markov decision processes. In fact, I will cover only the most, well, the first is the most widespread one, and the second, from my point of view, is the best in the qualities. That is, you can think about Merlin as a current state of the art in this field. So let us move on. So what is a Markov decision process? Well, mathematically speaking, it's a tuple. It's a tuple of 4, a set of states S, a set of actions A, and 2 functions. Mainly the state transition functions that gives us the transitions probabilities. That is the probability of the next state given current state and current action, and the reward function that gives us the mean reward conditioned on state and action. This the last part may be formulated in different textbooks differently, but it really doesn't change underlying proofs or anything like that. So in
What do you
addition,
mean by mean reward?
yeah,
It's not a reward. But
yeah, mean reward. The reward, the condition on state and action may be random. So it's yeah, you may have a probability on reward condition on state and action.
Don't you need to like have the full distribution?
Sorry.
Don't you need to have the full distribution?
No, for the proofs and the mathematical details, you don't have to, because what you are doing in a usual optimization and reinforcement learning, you are basically try to take a mean over all environment probabilities, and if there are some stochasticity in reward, or if there are not, it's not really matter.
But does it mean that the field never tries to quantify the stochasticity? Because if the variance is high, that's one thing. To like, for example, like quantify speed of convergence. Because like speed of convergence like really depends on the variance.
Yeah. I just said that there are for the last point there are many different variations of this definition. So yes, there are many different works concerning the risk-averse reinforcement learning that inevitably need to consider the stochasticity in rewards. So yeah, it's a good point. Thank you. So on the right there is a causal diagram of the Markov decision process. That is, that diagram shows us what nodes influence what other nodes, and this causal diagram will be different for partially observable Markov decision process. And so the Markov property that's probably is not very relevant to us today. But nevertheless, Markov property is a statement about conditional independence of the future state, of the next state, that is t+1, and the reward condition on state and action. And by the Markov property, this value is equal to it's independent of the all previous history. Previous to the time point t. So okay, I have told you that I will give you one example, and this is the most practical one I have managed to find. So this is about Atari games, and what do you think is the state here?
Image?
Positions of objects and their velocities.
Image, positions and
Velocities.
Any other?
Okay.
Sequence of pictures. Maybe for
Sequences
Yeah,
of
full
pictures.
sequence of pictures.
Okay, the whole
From the
history.
very start.
Yeah.
But like from the one thing, from one image, isn't it like
Yeah.
for past images.
Yeah. In fact, the most probably the most widely known limitation of Markov decision processes is that given only one screen of any Atari game, this process is not Markov. It's not a Markov decision process if you give an agent only one image per time. So what is usually done in reinforcement learning when someone plays Atari games? Usually these frames are stacked 4 at a time. So probably the first order Markovness is fulfilled, and an agent really gets fully specified Markov decision processes. But in its very essence, the state isn't the 4 frames stacked together. In fact, it is 28 bytes of unobserved Atari simulator RAM. And this is the state for any game in Atari simulator.
So you mean that the whole Atari simulator takes 128 bytes?
Yeah.
Like with the whole code? Oh, it's not code.
It's
like,
a state.
It's a state.
It's a state.
So, and it is a specific place in RAM.
Yeah.
It is there.
Yeah. So, in the real life, there are much more different sources of uncertainty. You're not concerned with playing dirty games unless you're absolutely dedicated to this field, man. In fact, what you're facing in every time in the world, any robot you can imagine will have some limitations. For an agent to operate, I don't say optimally, but close to optimal, it should measure not only itself, it should not only know who is him and where he also need to know where he is. So he should measure of environment, and he should measure himself, right? And in each of these measurements, some of the uncertainty may be present. So the uncertainty may be present due to imperfect self-sensing, due to imperfect environment perception, or an incomplete observation of environment. And more to say, when you are training and reinforcement learning agent with some function approximation, say with a neural network, you inevitably fall into a trap of partial observability, even in the case when the actual states which an agent receives as input are from the Markov decision process. That is because when you start your learning, your weights of your approximator are not optimal yet. And that means that any intermediate representation in the network does not fulfill any Markov property defined on the two previous slides.
But isn't Markov property usually encoded by the structure of the network? Say you just you define what the state is, and you just read that state, and network has access only to that.
Right, but when you are making final choice of which action to make, or where when you are deriving the probability distribution on the very top of your network, you are using the activations from the previous layers, right? And if your network is not fully trained with suboptimal weights, you receive on this previous layer some mass, right? It could be anything. It could be.
Imagine if you have a recurrent network and it's conditioned on the whole history, and recurrent networks are known for their separation. So despite the fact that formally your agent has access to its entire history, the final layers that make decisions only observe some finite number of states.
But that's the problem of the model. The model of the agent is not good enough. But it's not. That's not.
Yeah. I say exactly this. This problem is only because you use some function approximation, and this is part of your model. Okay. So how can we incorporate this uncertainty into decision making? How can we cope with this problem of additional uncertainty in our estimates? Well, the one, probably the most well-known way to do this is the partially observable Markov decision processes. And this is a mathematical model, a mathematical abstraction, and it's really very powerful and very widespread among the applications which were some time ago, I mean from 5 to 10 years ago. And this is because almost all of these papers deal with the planning. They do not deal with learning in a partially observable Markov decision process. And the learning is a very difficult task. So to give you some intuition of what the partially observable Markov decision process is, here is a table.
Can you explain what distributions these models receive as inputs, as not known ones?
Which one? Which models?
Typical models that work on planning.
On planning, yeah. let me do this in a way in a second. Okay. So in a partially observable Markov decision process, the states are not observable, observed completely, and it's. I think it's easy to understand. And the second axis on which we classify these models is of whether we have control over the state transition, whether our agent can influence which state he might go into the next time tick. So, the partially observable Markov decision process is defined is almost the same way as an MDP. Two more terms in its definitions appear, however. The capital omega and the O, the function O. The capital omega is a finite set of observations. And this talk we will say that this omega will contains only a finite number of observations, and we will not going to talk about the cases when this omega will contain, say, infinite number of observations. And the calligraphic O is a function which is called observation function, and this is a function which gives us the probability of observing this observation O for each next state and each action done. So to make sense of this definition, please look at the causal diagram. This causal diagram differs from the MDP's one only through the part which is highlighted in red. So in this graph, an agent is allowed to observe O, an observation, but is not allowed to see what state he might be in currently. And what do you think? Why this observation OT plus 1 depends not only on state, but also on action A, the previous action? Why is it that this is the case? Because if I say that the process is partially observable, and I say that there are some states, these states satisfy the Markov property, and the only problem I'm concerned with is that I cannot observe anything. So I can observe all of you, but I cannot see what's behind me, right? It's not dependent on my action. Or is it? Sorry?
If it's true, it's very easy because you can do it, you use it. And if you can make some action to see what's behind you, then it's more difficult to make a decision.
Yeah, right.
But maybe if you can change, if your actions can influence the state, then you can change the state, and then through that you will be dependent on.
Your position is not considered as a part of state here.
Sorry?
Is your position considered a part of
state?
Not the position, direction you are looking at. Is it part of
Direction
state?
I'm looking at. No, I guess no, because my position, my x and y in this room is my position. It's my state, right?
And direction, orientation in 3D. Like,
Okay.
If you close your eyes, you won't see anything.
Right. So,
in this formalism, we can remove conditioning of next observation on our action if we make our state space rich enough.
we made state space rich enough. Well,
because let's
when
say
You can always say that you can store your action in the state. So
action in the
That's
state.
yes,
That's
you just
very
augment your
good.
state with an action.
yeah.
Okay, but then you need to modify the transition probabilities in the way that the Markov properties is satisfied. And if you can do this, you're probably okay. So one of the possible explanations for this arrow from A to O is that pretend you're a robot and you're looking straight ahead, and you are in a state which is coded, as I have said previously, by x and y in some map. Now, this is your state. You know it for sure. But because a robot have some restricted, very restricted measurement system, it can only look with some angle. Okay, it can look only forward or only to the right, and only to the left, and from the direction in which he chose to look at in the previous time step depends on what exactly would be available as observations on the next time step. So you can think about this as just a detail and not very interesting one. So the first thing that comes to my mind is that why do we care about this partial observability? What if we ignore this property at all, as a whole? Say this observation is new states, and let our agent do the same thing that he previously done with the market decision process. So what I ask you for is the following question: what do you think? How bad can we end up if we just pretend that our action in a partially observable market decision process will be influenced? Action selection will be influenced only by the current observation and nothing more. How bad our agent?
In Bond, we don't know what direction.
You forget
I will forget anything, but why? Forget all the previous history.
What direction ball is moving. So,
But like, can you do the same? Like, if you just in your observation, you keep all history of your observations. It's not all history of states, but all history of observations.
We don't want to store such.
So by our assumption of a partially observable market decision process, the next observations depends only on the state and the previous action. So we cannot embed anything to it. So let me guide you through this interesting example. So pretend you're analyzing what is called adapted policy. Adapted policy is basically what I have just described. It's basically a policy which acts only on observations and nothing more, nothing less. Only observation in, probability distribution over actions out. So interesting to note, there are two intuitive facts about such policies. If you consider such deterministic adapted policy, and also say that every policy we are going to talk about now are stationary. That is, who knows what is stationary? Stationary policy? Basically, okay. A stationary policy is a policy which, given the same input, outputs the same output, irrespective of the time step. Okay, so the first assertion is that if you consider a deterministic policy and think about it in a partially observable market decision process, you will finally end up with an example where this deterministic policy can be arbitrarily bad compared to the best stochastic adaptive policy. So this is first intuitive.
The best deterministic policy possible?
Yeah, the best deterministic policy in partially observable market decision process. So not only policy, but an adapted policy that is acting only on observations. Okay. So why is it so? Can anyone tell before I show the answer?
Famous results in game theory, for example, if you're playing poker and if you're making always the same moves, it's easy. Your adversary can easily beat you.
Your adversary.
Well, poker everything very difficult because theoretically, it can happen that in poker there is optimal game theory strategy, and that's work. But it's not proven.
But I don't know what's the name of the game, like rock, paper, oh yes, rock, paper, scissors
Yeah, that's
is an example.
Okay. And what?
So-
Our rewards can like give us some intuition about the true state space, and we can like choose the point the policy operates good on rewards.
On rewards.
Without,
But our policy, doesn't know anything about rewards. It can only act upon the given observation. It is defined as a mapping from the from the space of observations to the set of probability distributions over actions. So probably the simplest example I know is this one. Present this A and B circles are states in a Markov decision process. And this Markov decision process satisfies the Markov property. But in a partially observable POMDP, you have this huge ellipse, which correspond to the single observation. So in this POMDP, these two states are perceptually aliased. So you receive the same observations for each of the state. So if you consider only adaptive policy, you are restricted to act in the same way in this state and in this state, because you cannot tell the difference between them. And the deterministic policy, what reward receives the deterministic policy here? Sorry?
Minus R.
Minus R. Any other ideas? Well, actually it receives minus infinity. Why?
I mean in one step minus R.
In one step, it can receive plus R or minus R, depending on in what state and what action you choose to make. So, the deterministic policy basically can start from any state, and after receiving a positive reward that is plus R, it loops infinitely in a state 8, for example, and receives for each action A made the minus R. So it receives an infinitely negative reward, and some of these rewards will be close to minus infinite. However, if you're thinking about the stochastic policy, which is given the same environment to act, what can this stochastic policy do? What is the optimal stochastic policy for this problem?
0.5?
0.5? Yeah, right. 0.5. 0.5 is the probability of making action A when receiving these observations, that observation that corresponds to any of these states. And this strategy will receive the sum of rewards close to 0, right? And that proves the first claim. The second claim is about the stochastic policy that can be arbitrarily bad compared to the optimal policy in underlying Markov decision process. And this is also rather intuitive, because the optimal policy, which can tell the difference between two states, can always select the action which leads to the positive reward. So, okay.
Sorry.
Okay.
And I didn't understand what this mean. So can be for some class of POMDP, or for E, or you only if you because provide example of such POMDP. Or it's always for any game we can state there.
This class of policy that I'm talking about now is not what is actually used to act in a partially observable Markov decision process. This is a simple illustration of why we cannot act only on observation space. Why we should do something more clever. And that's it. Okay. Okay. Another question for you. What maximum return is achievable for a non-stationary pulse? Yeah. Plus infinity, right? And that thought that we can extend our space on which our policy makes its decisions with time, and only this time will allow us to act optimally in this partially observable Markov decision process. But the space of non-stationary policies is very hard. We will not deal with it, and I haven't yet seen any papers or any books in which non-stationary policies were analyzed for a partially observable Markov decision process. In fact,
also like in this case, it's kind of, say you have like your optimal non-stationary policy, but like you still cannot disintegrate the actions. Then
Yeah.
like how to know which action do you start at? So if you shift it like with one, then you are screwed.
but yeah, you can always, you can always, if you have an access to the time access, you can always take modulo 2 and see whether you are on even or odd time and make decisions based on that. So the thought, the main point I want you to thought on is we need to extend our space on which our policy will act. And how do we do this? We can do this in many different ways, but there are some mathematical results which say that there are some class of sequences which is called a sufficient information process. And this sequence is, in fact, everything you can get out of your partially observable Markov decision process. So consider at first a complete information state. A complete information state is a tuple which is in which we have the distributions over initial state. We know it, and we have all of the history from time step 0 to the current time step t. And this will be called complete information state. So now sequence IT defines a sufficient information process when the three points are fulfilled. First point tell us that we should be able to update our information state, right? IT. And make this update depends only on the previous information state, on the current observation, and the previous action. The second point tells us that when we act, when we have this information state IT, and replace with this information state the complete information state, we should not lose any information about the future state, about the ST. And the third point is about not losing information about next observation, given our information state at time t-1, and also the previous action at-1. So this may seem rather formal.
What is the difference between LT and LTC?
LT
And LTC.
What is
I.
It's I. It's IT.
ITC. IT and ITC.
ITC is a whole history.
And
The whole history, like you're concatenating all that your agent have seen so far. And the I subscript T is some construction, some mathematical construction, which we hope will be of a less complex representation. So we don't want to store the whole history while the agent plays. And want to store some minimal sufficient information, minimal sufficient statistics. And I cannot say this is a theorem, but the set of conditions in which we can throw away all the history we have obtained so far and stick only with our I sub t as a descriptor of our current position. So let's go through the example. Let's pretend you have a robot, the small red robot, which acts in some terrific domain. And at the first time point, this robot believes that he's somewhere before this brick wall. He doesn't know where he is, but he has a map. He has a map of this wall, and he also knows that if he observe the door, he might be only in front of one of the three of them. And the first, this graph is tell us what is the probability of such observations of observing the door given some x, some state. And this the lower graph shows us what the agent believes now. Then the agent moves to the right and also sees the second door. Now he knows that the door can be present only in 3 different positions. And by this process, the agent finally managed to know what is his state, right? With large probability. And this is just a toy example, but the main thing which we are to go through is the notion of belief state. So the belief state is defined as the probability of belief state is defined as the probability distribution over the state space. Okay? So intuitively, the belief state is in what state agent believes it is currently in. Okay? Okay. So there is a nice theorem, an old theorem, which states that partially observable Markov decision process is actually nothing but the simple Markov decision process if we properly update this belief state. And this belief state is exactly what we were talking about when we defined a sequence I of sufficient information process. So properly updated belief state satisfies all these properties. And what I mean by the properly updated belief state. So the updated belief state B prime of some state S prime is defined as a conditional probability of staying in state S prime, while if we begin our process in the belief state B, make action A and observe O prime. Is it clear for now? Any questions? Okay, everything is taken apart.
Can you clarify what are A and B?
What is A and B? B is a belief state on the previous time step. So you can think about B as B sub t, right? And B prime as a B sub t plus 1. Okay, the next, the update belief state.
Okay.
Okay.
And A is action.
And A is action. A is action and O prime is observation. The prime, usually the prime stands for the next, for something that is next. The next state, the next action, the next observation, the next belief state, and so on. So, by definition, it's just a conditional probability, and this conditional probability we can rewrite. We can use just Bayes' rule for this conditional probability. If this is it clear? How? How do we get from this to this?
Oh.
Yes.
Yeah.
This is a distribution conditioned on distribution.
Yeah. Yeah. Distribution conditioned on distribution, and it may be scary for the first time, but you will get used to it. Okay. So the whole other two lines is just application of Bayes rule. So we rewrite our enumerator as a product of hitting the next state S prime. So this term is the probability of hitting S prime if we start our action A in state B. Okay, and this probability, that is the last term, can be rewritten as the joint probability is a sum over S of a joint probability P S prime S. Right? So we marginalize the joint density over all possible states in the moment we made an action. So what is the intuition here? We don't know in what state we are currently in, but we know that we might be in any of the possible states with some probability, and this probability is a belief state probability. And we also know, by assumption for now, that we also know the transition probability. So what is the probability of transition into the next state S prime given action A and state S? And that's it.
So why do we have B prime on the left-hand side?
B prime stands only for the updated belief state. It's just
so this is kind of a Bellman equations for beliefs.
Bellman equations for belief? No, I guess no. The Bellman equation for belief will be on the next slide. But on this slide, what we are talking about, we have just considered the set of conditions which need to be fulfilled for us to throw away all previous history and use some sufficient statistics of all the history, of all the data we have gathered so far. And this belief state and the update, this date of belief state is the one possible information state which fulfills that three conditions. Okay? Okay? Anyone? Someone?
What is the difference between big P and little p? Is it the same?
That's a good question. Yeah, they are the same.
It's just probability.
It's just probability.
How does it follow from the definition of VT of S, that is probability given ITC? How does it follow the first equation below?
This one.
Yeah.
This first equality is just a definition of belief state.
But it's a redefinition.
Okay, let me see. No, it's not. It's not. So consider the initializing your belief state as a
Empty set.
empty set thinking, as an empty set. Okay, this is the point of time where you start your episode. You have no previous information. So in this case, these definitions. What tell us this definition? This definitions tell us that the belief state is a conditional probability of current state being equal to S, conditioned on the all previous history. And the all previous history for now is only composed of an action which we made in the time step t equal to 0, and the observation which followed that action selection. And this is all prime. Okay?
So
This is, okay, let me.
is it somehow follows from the fact that belief state is a sufficient information process?
Yeah, it is sufficient information process, and this question was a little bit different.
So
Right.
what is O?
The O is the observation. Let me go back. The O is an observation. That is some random variable which depends on the state which an agent does not have access to, and on the previous action that the agent have made. Okay. Okay. So we have defined a complete information state as a sequence that is composed of all the previous history plus some initial distributions over initial state. And you can, in this first equality, you can easily map this term to this term by assuming that the initial belief will be the initial distribution over states, just as I showed you on the previous slide, the uniform belief over all possible state spaces. And the A and O prime is history, is this guy. The old history collected.
But it seems like it uses some Markov property.
Yeah, it should
Right.
use some Markov property, because the partially observable Markov decision process is actually is actually a Markov decision process, because the states to which our agent has no access fulfills the Markov property. And the only problem we need to deal with is that our agent is not allowed to see this state.
I see. So it follows from the Markov property.
Okay.
Okay.
So
how this theorem states that you can convert a given PO-MDP into a usual MDP, right? And in this usual MDP, your states are these beliefs, B prime.
yes, and these belief states are continuous.
Yeah, and so kind of do you really observe something out of the environment? Like how would you even incorporate the knowledge you get out of the environment? I mean, you do some action, and it somehow changes the environment. So how do you incorporate the response from the environment?
Yeah. This is precisely why I have shown this example. So this guy is acting in a partially observable Markov decision process. It doesn't know anything about the initial position. You have a uniform prior, if you want. Now he observed a door, and by observing this door and knowing the model, the observation model, right? That should be O in our notation. So this our agent can use this additional probability of observation given state to find in what state it is currently in. So this picture tells us that if an agent observes the door, he might be only in 3 possible states, right? And when acting further and observing further door, he now knows that with high probability he is in this point, right? He is in this X. And this is a way an agent could make sense of the observation that come into its sensors.
Well, the problem is that the agent has to have access to the map, but in real life problems there is no map. We don't know how the state
and we also don't know what is the probability of observation given state.
Yeah.
And we also don't know what is transition dynamics between states. So we don't know anything, in fact.
So how could we apply it?
So let's see, how can we apply it? But before we see,
do we need to know the initial state distribution to update our belief distribution?
Well, Ian, there are two answers. If you can, please do it. And the second is, in the long run, when you have unrestricted access to your environment, or
it's close to the state share.
Yeah, it's irrelevant, and it's irrelevant again because the bias form. Yes. So we know what is the Bellman optimality equation for V star in the Markov decision process. If you don't know, it's okay. Here it is. And this equation is one of the fundamental equations in reinforcement learning, and it's a discrete in stochastic optimal control. And this equation is you can show that this V star is a contraction mapping, and if you apply many updates, that is apply the fixed point method.
Fixed point iteration, yeah.
Fixed point iteration. Oh, no, I don't think so. Because fixed point iteration, fixed point is fixed point, and you can iterate in fixed point in many ways.
So if it's contraction mapping,
you can apply
implicit methods, explicit methods. A fixed point is that new and old.
Okay, I will see. So what? How can you reformulate this Bellman optimality equation for V star when your states are now replaced by belief states? So now every state occurrence in this formula we replace by belief, and also we now need to make sense what is the reward of BA and what is the probability of the next belief state given current belief state and current action.
The sum is still over S prime, or it should be prime?
Oh, yeah. Sorry, this should be B prime. I overlooked it.
It should be like an integral, sum over distributions.
Right. Thank you. So the way you can reformulate this to highlighted guys. So this one and this one is probably not highlighted, but it's highlighted here. What can you say? You can say the first that the reward that's as the function of belief state in action is nothing but the expectation over all R of S and A over the distribution that is our belief state, that we call it current belief state. And this transition model over a belief state can be also written as a joint probability of current state, the next state, the next observation, and the next belief state, averaged over current state, the next state, and the next observation. And this is precisely what stands behind the assertion that the partially observable Markov decision process is a Markov decision process on the belief state. Okay, so yeah.
How can we sum over by prime? Because we should sum over all possible updated distributions, belief distributions.
Yeah. Yeah.
Oh, yeah.
And this is exactly the reason why this.
I mean, mathematically.
No, I mean this is just an integral, not the sum, but
This is an integral. Yeah, you can.
If you can compute all the quantities involved, you can surely.
Okay,
integrate
pretend you have
space of
pretend you have
distributions.
Yeah.
Alexander. Pretend you have only two states. So your belief state is of dimension 1 because the belief state is a probability of being in a state 1. Say for example, the other probability of being in a state 0 is obtained as 1 minus.
Forget about the finite set of observables.
Okay. Okay. So we are to move forward. So the bad news, as you have already spotted, is that belief updating is can be made exactly only for some specific cases. One and second, even if it can be made, the resultant Markov decision process is not very easy to solve. It's not exactly the Markov decision process we are used to in Atari game or Go game or some other game. And these two cases in which you can make the belief update precise are very restrictive ones. So the first case is when your state space is discrete and very low dimensional. So this the belief state, the update of belief can be made in this case exactly. The second widely known case is the case of linear Gaussian dynamics. And this linear Gaussian dynamics, for the people who are not come from reinforcement learning community, is known under the name of Kalman filter. So the Kalman filter is exactly the way to recompute the belief state. So update belief state condition on our current belief about state, about distribution over states, and some observation. And if you assume that your next state is some probably noisy function, linear function of current state and current action, and also if you assume that your next observation is also some noisy linear function of state S prime A, you can again update the belief state precisely. The third line is almost you can forget this line, but if you're interested in why is it here because this linear Gaussian dynamics is widely known and widely studied in the stochastic optimal control, and in stochastic optimal control this assumption of the reward being the function, the quadratic function over state and action is a crucial one. Because in that case, you can analytically, starting from the very end of your process, from your goal, you can apply dynamic programming and solve for the action you must make now in current state. In current state to move to the goal. So, okay, now we are getting closer to reality.
So about the linear Gaussian dynamics, how do the belief updates actually look like? I mean, these are distributions or distributions over states?
Well, in fact, do you know how the Kalman filter works?
Yeah.
That's precisely the Kalman filter.
No, I mean,
this O prime is a emission. This is emission. This distribution.
Can you step back one slide? Okay. Back. Yeah. So here you have probability of B prime given B, and B itself is a distribution. So you need to model a distribution over distributions. B is a distribution over a state over continuous value.
Okay, so let me clarify a bit. this expression is nothing but theoretical construction. It's not used in practice because it's intractable almost always. Unless you're in...
Yeah, but you just said that in case of linear dynamics, you can...
Okay, in case of linear dynamics, this indicator. This indicator is always equal to 1 because this bias filter update is made analytically because you have the conjugate, the two normal distributions. And these terms cancel out. And what do you have left? You have the expectations over normal distribution or your previous belief state with some parameters you have pre-computed on the previous time step. Of some what? Of some of the Gaussian density and the Gaussian density.
Okay.
With some known parameters that the linear functions on S, on A, on S prime, on A. Let me this one. So in the most basic assumption, the most basic versions of this task, you assume that everything is given. That you know any matrix here, including the sigma matrices. And it's, in fact, it's very, you may think that it's very restrictive because in practice it is never, it's never fulfilled. So we in practice don't have such knowledge. But in practice, in physical systems, and when you think about robots, these equations are more or less satisfied. So you can estimate these matrices, but this is another talk, not today's talk. But in reinforcement learning, in partially observable market decision process, we need not only to deal with unknown dynamics, we also may have states being of a very complex nature. They may be images, they may be some large vectors, and so on. And the state transition function may be non-linear and may be completely unknown. So what can we do in this cases? The possible options are as follows. So we can use, the first one, we can use very advanced tracking techniques. We can apply some non-linear version of Kalman filter if we have some suspicion that our model, our state transition dynamics is more or less linear. If not, we can estimate this function in addition to simultaneously solving the tracking problem. So the tracking problem is the problem of keeping this belief state, which for guys not from reinforcement learning community, this may be known as a posterior over hidden states.
As I remember in that paper, they just rotation MNIST experiments.
No, there are no MNIST. There are two bouncing balls, in which they are allowed to bam, 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 bam. Yeah, and the dynamics behind this bam 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 is non-linear. They in this paper they try to simultaneously learn what is the state under this under the visual representation of these balls, and to estimate what is the transition function between states under this.
So real states are considered like variables?
Yeah. Real states are considered like variables.
And all the normal stuff like rational encoders implies, yes?
Yeah, more or less like.
And is there any actions or no actions? Just
Yeah, there are actions. There are actions at the as an usual Kalman filter. There are actions which are denoted by U, in these papers. So let me move on because there is so much time.
Just the
Yeah,
last
okay.
question. What is their what parameters are observable there? Like, for instance, you said that this pulse.
Okay, the only one thing that is observed in this direction of scientific literature is X, is your observations. But you believe that X is emitted. Your X is emitted by some latent variable, Z, say Z, and you need to estimate the probability of transition between these states and the probability of emission this X.
So that we're trying to do some kind of variational encoders where X is all history of our observations and our actions.
Yes, all history of our observations. Well, not exactly like this, but you're very close to it. So please see the paper, or come to me when this talk is over. So the second option is a pretty decent one. So just forget all I told you about and use some recurrent network in your architecture for deep learning deep reinforcement learning agent. And that's a rather popular direction. So another option is to preserve information in this is to do no belief checking, no update, no belief update. But while you're using this recurrent network, you are enforcing your recurrent network to preserve information in activations or in the cell state or in some output hidden state. You ask that this state should be of great utility to predict future states and future activations. So again, let me go back for a moment. This is what I'm thinking about when I'm telling you about the predictive state distribution, state representation. So if you can predict what the next observation will be, it means you have internally in your recurrent neural network, you have sufficiently much information about what is going on under the hood in the state of your Markov decision process. But this is again not what we are going to talk. The last point is the last option is to use a human-like differentiable memory, and this is more or less the very recent works. The first one is published in iClear, 2020, which will be in 3 weeks. And the second one is, I guess, 1 week old on archive. And what we are going to talk about the first set of methods, which just replace your policy from Markov decision process with some recurrent policy, and we are also going to talk about this Merlin, about this magic method. So the deep recurrent Q-learning is the first method of the family labeled as forget all the math and just do deep learning. And it's in fact it's easy. It's very easy because in Q-learning we need to estimate the Q function, and the Q function depends on state, obviously. This state we don't know what this state is, but we can pretend that we have some memory that is h sub t, and we can approximate this Q of S and A with some Q of observation the previous memory state, and the current action. And we can also eliminate the dependence on current observation by just modeling this our memory HT as an LSTM with input the previous hash as input, and also the current observation as input to this LSTM. So this is that simple, and this is one of the benefits of this method. We need only to model this Q function, which will be a recurrent neural network, and literally the changes to vanilla DKN architecture are almost zero, right? All the thing you need to change is previous to last layer, because it's replaced dense by LSTM, and also change this 4 stacked frames, replace it by one frame every time, and that's all. And your paper will be published. Okay, so we are.
How many? In order to train this thing, you actually need to take some trajectory
right.
and feed it through the LSTM and
right.
hope that your gradients propagate all the way to the beginning.
Yeah.
So do you happen to know the details of how they did the training? Like
yeah.
How much, how long history they actually put in there in the recurrent neural network?
Yeah. Yes. There are so many details under the hood here, because to train your DKN agent, you need to train it on the very large data. So you need to collect all of the previous experience in some sort of experience replay, some sort of history storage. And in this history storage, you to increase the sample efficiency for you to finally get something useful at the end of the weekend learning. And this sampling from this experience replay is really a very difficult thing, because in the recurrent architectures you have a memory. So you cannot sample only one transition, as is required for updating the Q function in the usual markov decision process.
Yeah, you need the whole trajectory.
Yeah, you need the whole trajectory. And when you are sampling the whole trajectory, you end up with very correlated updates. So every update that you are making, let me clarify. Pretend your agent managed to find the rock, and literally as hid hide this
hide under the rock.
Yeah, it has been hidden under the rock. Okay, so and now you sample this trajectory, and all this trajectory contains of say 10 million ticks of an agent of being under the rock, and that's all. And you are updating all again and again your Q function, and you finally learn that being under the rock is rather useful. But
nice.
when this
is it true for completely observable for
yeah, it's true. It's exactly true, and that is because in your experience replay you are not storing the whole trajectories. You're storing only one-step transitions. And when you're sampling in your usual markov decision process scenario, you sample at random these one-step transitions across many different episodes. But when you're learning your recurrent agent, you need to initialize your memory, right? And that is a problem. So there are some hacks to solve this problem, mainly to sample not the whole trajectory and not the only single one transition, but sample say the piece of say 10 subsequent steps, and that half of this piece just updating. You're not updating your Q network, but you are learning the hidden state. You're learning the hidden state for say 5 time steps, and when you have some learned some properly initialized hidden state by this five-time process. You can spend the last five steps updating your Q network, or updating your parameters.
It's like estimating the stationary distribution of the states and then rolling your simulation from this?
No. This has nothing to do with stationary distribution of your states. So we can talk it. We can take it offline. So what we have seen already. So pretend we need the super intelligent, super powerful agent in the future, which will receive an input image, which can determine its velocity, which know what is how good his previous action was, and to which we can tell what to do next. And this slide represents the architecture I have already covered. You have some previous action, which is considered as one of the elements of your observations, along with input image, agent velocity, previous reward, and text instructions. This constitutes the O vector. By encoding this O vector into some intermediate E vector and using some RNN-like architecture, you may finally learn something useful in reinforcement learning. However, there are some drawbacks. These drawbacks are almost fatal. You have to use the truncated backpropagation through time. This truncated backpropagation through time will not allow agent to learn anything that is more distant than your truncation length. And again, the reinforcement learning is hard because the supervising signal, that is the reward, are very sparse. And you are assuming that you are learning your agent, learning the parameters of your agent from this sparse signal. That's not the best thing you can do. The one-step improvement of this architecture would be to equip your agent with some human-like memory, with some DNC-like memory. That is a differentiable memory tensor M, in which you can write and read in proper times. And these times and what to read and what to write is determined fully by the reinforcement layer's loss at the top of your deep learning agent.
Why do you call it human-like, not computer-like?
It's like attention.
Because differentiable, human-like memory.
Okay. Okay,
That's how you get in the publication accepted beliefs.
No. We will talk about human-like in 2 slides. For now, okay, this is a computer. It's just computer mess again. So the work about which I want to tell you is Merlin. Merlin is basically the cool paper, which is, by the way, 57 pages long. And what? Yeah, and it comes from 24 authors from DeepMind. And its main motivation of this paper is that all of the motivation of this paper comes from neuroscience. So they say that humans use inside their brains, they use predictive sensory coding. So their brain continually generates models of the world based on the current context and on the previous history. And it does so to predict future sensory input, to predict what it will see next. The second motivation is about something called hippocampal representation theory. And this theory says that representations inside the brain, inside the hippocampus, pass through a compressive bottleneck and then reconstruct input stimuli. And these reconstructions, unlike in the usual variational autoencoders, is done together with the task reward. So it's the reward also influence on how this this information from bottleneck is reconstructed, and it's in fact a crucial difference. And the third is the temporal context model. So the temporal context model is just about using time. It's just about not forgetting about it and assuming everything is Markov. And under the hood of this paper, there are mainly three main components. There are variational autoencoders, there are differentiable neural computer, and recurrent asynchronous advantage active prediction. These three components are mixed together to form this.
So that is why 24 authors.
Yeah.
Authors from each block.
Yeah, of course. Each author is responsible for each and every arrow here. So it may seem very complex one, and it in fact is. And it is because this paper is 57 pages long. But the main I will try to summarize this paper very briefly and to give you an intuition of what's going on. So you start with some observation vector, and observation vector they used was composed of 5 components. That is an image, the velocity of the agent, previous action, previous reward, and the text instruction, as I said previously. Now, this vector is of size 10,000. This vector, each component of this vector was independently encoded into some another vector. We will call it E sub t, which is of much smaller dimension. And each component of this vector is encoded with its own network, its own 6 resonance blocks for the case of image, and for the case of action and reward, there are no encodings. And also the decoding process needed for variational autoencoders uses the same architectures. And the one thing that is not usual for variational autoencoder is a return predictor decoder. This guy, what does this guy is doing? This guy is modeling the value function. That is, value function is a mean return from the current state, which is here denoted by z, until the end of the episode. And it is regressed. It is regressed on the Monte Carlo estimates of return. And it also depends on the current latent state, the z sub t, and also on the logits of the policy. The policy which actually makes actions. Another function which is also decoded from the z state, from the latent state, is advantage function, and it is regressed on the difference of the Monte Carlo return and the predicted value function of the current hidden state. That's probably not so hard for now, but we are moving forward. So the main interesting point here is the memory. The memory is a tensor with two dimensions. The first dimension is some fixed n. This is the number of cells in your memory, and the second dimension is twice as large as the hidden vector. Why twice? Because we are going to store in this memory 2 quantities, each of the size of z. The first is z itself. We are going to store z in each and every moment. And the second quantity is a so-called retroactive memory. That is a mean latent vector when the mean is taken from the point now, from the point t, from the time step t, and the end of an episode. So you in some sense, you're taking average over all future observations. Observations in the sense of the hidden state, hidden latent variable z.
Don't you store in previous information?
Store any previous information? Well, no, because I will store any z from the at t equal to 0, I will store z0. At t equal to 1, I will store in my memory z1, but I will also store this guy, or only one guy of this, right? I will store gamma to z1. Then I will store in my memory z2, and I will sum this one as follows. I will multiply it by gamma. I multiply by gamma what is currently in this cell, and I will add some C2 to this half of the cell. And I will do this process for each and every cell as I move forward. And I will talk a little bit about this process in a while. So the main thing why this may be useful because you are training with the reinforcement learning agent. So the amount of supervision signal is very scarce and very little. And you need to store as much as you can. And this way, this mean future embedding, I will call that as latent embedding, is very useful for an agent to understand which future state it will execute.
Can you draw this standard virtually example and visualize how it evolves over time?
Draw what, sorry?
Can you draw how it changes over time? Because I completely lost clue of what's happening here.
Okay, it's normal. It's normal because it's 57 pages long. Let me go through it from the scratch. So you have an observation vector OT. This is clear. I suppose it's clear. You're encoding this vector in some latent in some smaller representation vector ET, and then the difficult. Then the magic happens.
Answer is still clear. Okay, it's just.
Yeah. So for now, assume you have some prior in your latent space. In the same way you have it for autoencoders, right? Okay.
Prior on E.
Prior on E.
Okay.
But exactly not on E but on T, but this is difficult. Say on E. For now, say on E. You also have some posterior distribution. We'll call it K, and we'll also model this posterior distribution in the same way as we do it in variational autoencoders.
Posterior given all history.
Well, not exactly all history, but
recent time steps.
Okay. Because this queue uses some recurrent architectures along with the reads from the memory, and that isn't a very simple thing.
You still learn history with LSTM.
LSTM.
Right? So history you learn H substrate T.
Okay.
So
with LSTM.
HT is LSTM, right?
Yeah. Okay.
Because this is also LSTM.
Yeah, and then you use it to figure out your memory. And you use both memory and history.
Memory and history. Well, okay.
So what is latent variable is trying to represent?
what the latent variable is trying to represent.
What we are trying to encode using our encoder? What is it? What are the inputs of our encoder?
What do we hope that our architecture will encode into the latent space?
Yeah.
We hope that this latent vector z, which is here, which is a sample from the posterior, we hope that this z will carry important information needed to make
hippocampal memory.
Yeah, all that stuff. Right.
Excuse me. Yeah. And does we have any information about the rewards in our memory or not?
And does we have some information? In fact, this is not a very simple question, because when you see the architecture, you see that there are no influence of your loss of your reinforcement learning loss on your memory, and that is the key point of this paper. They say that reinforcement learning loss is simply not sufficient to learn sufficiently good latent states which are which will be good for acting upon it.
As far as I understand, the part to the left of this red vertical is a simple variational encoder that tries to encode all these tuples to the left.
All these tuples to the left. Well, in some sense, yes. In some sense, no. Yeah, it's look here. It's really the same. It is a variational autoencoder, except that there is one more loss from it, and this loss tries to decode from the hidden vector z. It tries to decode the mean value function, not mean product value function.
So then we don't use any information.
Let me just continue.
Okay.
I will try to explain. Maybe I will fail, but
Do we learn memory with also neural network?
sorry.
Do we estimate the memory with some neural network as well?
The memory is fully differentiable. I will tell the.
Okay.
I will give some details in a bit, in a few moments. Well, it's very difficult to explain this architecture because almost every single component depends on the other one, and you cannot. You're in the closed loop. You cannot simply start and do not do any assumption of you that you know something else in this architecture. So I will explain that there is a memory tender, MT. This memory tender is a fixed size, and the second dimension of this memory tender will contain two components. It will contain the latent vector ZT, and it also will contain the mean over all future latent vectors. Next, we will have two components in this architecture. The first component is a model-based predictor. The second component is a policy. This policy uses memory as read-only. It does not write anything to it. It just read-only memory. So the memory-based predictor, it reads from memory and writes to memory. It reads from memory several times per step. In the paper, they used three times. So in each time step, they read from the memory tender 3 times. 3 read heads. How do they read from this memory? I don't know if I need to go through details, because you're a little bit tired.
Kind of more or less regular attention mechanism.
Not only you.
More or less.
Okay.
That's a fantastic note.
Is it similar to what is done in neural-Thielen machine?
Yeah, it's some simplification of DNC model, if you know what is it. Okay, and then this model writes to this memory, and also this you can see in the DNC paper if you are interested. But in the very essence, it does this thing. It writes each in each cell in this memory, and when it runs out of the empty cells, it starts to rewrite cells. And it rewrites cells based on the utility. This utility is simply how much this particular K cell was read previously. If it was read once or it wasn't read at all, we will simply rewrite this cell. And that's it. So the line and space. Here are the people who knows what is relational encoders could also see me what am I doing here. So in we are two distributions. We have prior and we have posterior, as in case of relational autoencoders. But in prior, in how do we model prior? We have some multi-layer perceptron that has ht-1 and mt-1. This guy is a concatenated vector of two LSTMs. One LSTMs of model-based predictor, this one, and the second LSTM is here. So the prior is defined on both of them, and it also receives as input the vector that was read from the memory on the previous time step as the time t-1. And it outputs some mu log sigma as in usual autoencoders, but it do this for prior distribution. We also have a posterior distribution, and on this posterior distribution, recall that I have said this posterior distribution does not depend on E, merely on E, but it's depend on N, and this N, is a concatenated vector of almost anything you can find on the time step T.
This memory, yes, again.
Yes.
We usually use this for the fulfilled episode because, as far as I understand, that memory, that the things that you write into the memory, they change with the time.
Yeah.
You add this gamma z1,
yeah.
etc., etc. So when you learn here, do you use the fully ended episode information, or you use some state that you do not know?
Yeah, thank you. Thank you. It's a good question. The answer to this is nothing in between. Something in between. Sorry, something in between. You don't want to update in the very end of your episode because the episode may be very, very, very long, and you also don't want to update just now because you need to, as I said previously, you need to learn the value function, and the value function is defined as a mean of subsequently generated rewards, and it cannot be updated now. So what you do, you are define some horizon t and say that I will update every capital T time steps, and that's it. Okay, so posterior is almost the same as prior, except it's posterior. I'm almost serious. It depends on NT, and it uses the prior parameters output by prior multilayer perceptron. So, again, that T is a sample from posterior factorized Gaussian, as I have said previously. And the thing, the way we learn this model-based predictor is through the variational lower bound. I will not go into detail here again, but again, it's if you know how to apply variational autoencoders for time series, you are done. It's nothing new here. So, and the most probably the most anticipated slide, because it is the last one. It's the slide with experiments. Let me say that they have 8 experiments in their paper, and almost any of them is quite impressive, but probably the most impressive experiments are these three. The first experiment is about goal orientation in a maze, and that maze is not just an entire screen or something like this. This is the real 3D maze with several rooms with corridors, and with some different goals that agent needs to pick, and with some different distortions of this environment. Why this paper is interesting? Because it deals with partially observable process, and it deals with it in the way that that is better than professional human testers. That professional human testers are the people who sit and test. They play games professionally. Okay? So they have in DeepMind. They have.
What's the DeepMind?
Maybe that's an easier way to get into DeepMind.
Okay.
Maybe you should be very radical.
So this task of finding the goal in the maze was solved by this agent better than this professional tester.
Okay, like a question, and like, can the system generalize to different?
Yeah.
Yes.
Yeah.
So
yeah.
That's
they have such experience in the paper. They
because humans can. Humans can generalize to different.
Yeah, they also can. They do in the paper many different experiments. For example, they delete all the surrounding walls. That is, they delete the skyline, so there are no horizontal skyline, and everything works good. They put obstacles in the corridors, and an agent found better than the humans found the goal faster. The second, let me show you another experiment. Here is an interesting experiment, again inspired by neuroscience. There is a famous experience which monkeys were shown some visual cues on the screen and were rewarded when they classified somehow these images. This probably this experiment. When you see this experiment, you might probably think that we are almost in the level of monkeys. So we solve this task again better than the humans, and that is quite impressive. So what's going on? The agent is shown some visual object on the screen, and all it can do is to move left, right, up or down, and by moving in the right direction, it gets rewarded. And again, according to...
Why is it partially observable?
Sorry?
Why is it partially observable?
Why is it partially observable? Because you probably need to remember what was previously... Well, maybe it's not partially observable. This one.
What's the right direction?
Sorry?
What's the right direction?
The right direction is defined for each object, and it has no meaning. It's just for the apple moves right. It's not my suggestions. yeah, it's not my suggestions. I have turned into incognito mode, so hands down, everything's okay. This last video is again about latent learning. This is a thing that please read on the next slide. So what's going on? Let me a little bit algebraically today. So the agent is put in the beginning of the T-shaped maze, and the agent is rewarded for collecting apples. And the apples are everywhere. They are here, they are here, they are here, but there are some other objects in this maze along with apples, and agent is not rewarded for collecting any of them. For some time, it's trained on this T-maze, and it is collecting apples and doing fine. And then it's put in the phase 2. In the phase 2, the two side rooms were removed, and only apples in the corridor were left. And again, it collects the apples. In the phase 3, it's again imposed to the T-mazed room, T-shaped room, and it is given in the beginning of this room the image of the object it should find in this maze. Interestingly, that while collecting apples, agent has managed to remember in which of these two rooms this particular object is located. So when an agent comes to the top of this maze, it has only one choice to go right or go left. In the case the choice is bad, the episode ends and it receives nothing. So the point which I'm trying to make is that agent, while collecting apples and being exposed to some intermediately wrong task of collecting apples in a long corridor, finally it still managed to remember in what room the particular object arises. And all of the zero experiments says that no LSTM or DNC learned on reinforcement learning laws can compete with this Merlin architecture. So for now, this is again not my recommendations. Thank you. If you're interested, there are some references here.
50 yeah.